Last time we were discussing about the structure of crystalline material. So we continue with that because I said other day, my ultimate interest in all that I am doing right now is to see how do I achieve control over this equation, which is essentially a statement of Ohm's law. Okay. However, later we shall say this is not the only kind of transport I am worried about. There will be something more which will actually dominate in many cases than the one which I am stating. So why we are interested in first one? Yeah, there is something more to it. The two devices which are of utmost importance for us in this course are bipolar junction transistors and a MOSFET. In the case of MOSFET, the transport is essentially drift transport. Essential mechanism of transport in MOSFET is the J sigma E, whereas in BJT it is essentially the second transport, which essentially called diffusion current. We shall see what is it soon as we come to PN junctions. So the first is drift current, which essentially is the major current in the case of MOSFETs, whereas in the case of BJT it is the diffusion current which dominates over the drift current and therefore more important for BJTs. Though we have not done anything on diffusion right now, so we will not go into details for this. As we progress, we will look into it. This is very dominant current in BJT and why we are so keen to know about it. Okay, so right now continuing with our thinking, and you will be also be giving some, this sigma, as last time we said, N or P, whatever number. This term we said mobility has something to do with the electrons moving in a crystal. If we are unimpeded, that means it does not get any hit anywhere. What are the possible hits it can have? It can hit with the atom itself or between number of electrons, because there are large number of electrons there, they may hit each other as well and lose their energy. And if they lose their energy, they will not move faster, okay. And if they don't move faster, we say they are sluggish. That's why mobility is lower, okay. So we figured out in a crystal that in certain directions, the mobility is higher compared to the other directions of the crystals. And therefore, if we are really looking for larger mobility, you can see from here, my ultimate aim is, this is electric field which is V divided by distance. So the thickness of the region where with which voltage applied. So I want smaller V, larger J. That's what our ultimate aim is, because then the power comparatively can be minimized. To do this, I must somehow get a relationship in which V and J are related in a simplified form, okay, and that's what exactly we are looking. So we are looking into this term very strongly, okay. And because of that, also I will say you later, though mobility is not directly seen in the case of diffusion current, but it is omnipresent there as well, okay, through a relation which is ascribed to a famous scientist, Einstein. The relation is called Einstein relation. So there is a diffusivity is related to mobility. So in some sense, mobility is of crucial part for our device currents. So we will look into it today. So just to give again always the brief introduction of why we are doing some things, and then we will look into the things which may or may not be as interesting as I say this part. Okay. Last time I said silicon, for example, has 4 atoms, 4 electrons in the outermost shell. The way silicon atom actually gets bonded is every silicon atom is surrounded by 4 nearest neighbors. Okay. Now this is called primitive cell and it is tetrahedral in nature and difficult to replicate if I translate in any normal, unless it is r theta phi kind of translations. It will be very difficult to replicate this kind of this to create full crystal. So we said, okay, why not look into a simpler cell which is like a cubic crystal cell which can be easily by Cartesian itself by R is equal to MA plus NB plus NC. We can always translate in any position to any position, and that's why we looked into unit cell. But unit cell is not the minimum cell. Minimum cell is a primitive cell which is of this kind. Okay. However, that means in unit cell there will be some, this structure must exist even in the unit cell because this is a primitive part. Okay, so if you see a silicon structure with atomic arrangement in unit cell, there must be some way you must see this tetrahedral there. Okay. Otherwise there is some problem in, because then it's not a primitive cell. Okay. So the trick is to get into this kind of arrangement which is simpler, and we last time discussed about cubic cell, I trust so, I did, and we said okay, FCC, and the face has, each face has one atom, and one is of course body center in which there is a one single atom in the center of the cube. So there are three possibilities of arrangement. We said simple cubic, then we said FCC, face center cubic, and then body centered cubic. So three possible unit cells are done in a Cartesian system which can be replicated easily to create the whole size of the crystal which you are looking at. However, as I said, our ultimate aim is not this. So we want to know how many atoms are where in a particular cell, and we want to know what is the density, because after all two things are of interest to us. One is how many atoms of silicon, or for that matter any other this, exist in a material per cc. That is, it's called density in some way, number density, okay, atomic number density, atomic density. So how many atoms per cc silicon has, or germanium has, or any other gallium arsenide, or any other semiconductor has. So this is very important for us, how many. Then we are also interested in actual density, which is gram per cc essentially, and described in a mole fractions, okay, by using Avogadro numbers. So we like to know whether the density is how much. If silicon has density, let's say 2.33, from where it comes, okay, or vice versa. If it is, how many is that atoms correspond to that number? So they are related, and that unit cell must be able to give us this number very easily. That's exactly what we'll do now, so that we'll be able to know how many silicon atoms per cc exist. To do this, let's look at the cubic structure first. We say every corner at least has one atom. This is simple cubic. Okay. And we say it has 8 nearest neighbor where each atom can share with it. So the total number of atoms in a unit cell is 1/8 into 8, which is 1 atom. When we said okay, if there are surface atoms in all 6 surfaces, one on the center, then there will be, each surface can only sideways only share, so half from that is 3 from the surface and 1 from the corner. So 3 plus 1, 4. And if there is only one inside cubic, then it is 1 plus 1, 2. So BCC has number of atoms 2, FCC has 4, and simple cubic has 1. So this number in a unit cell first we'll know how many. So we know 1, 4 and 2 are the number of atoms in a unit cell of single crystal kind of cubic cell which we are assuming. Just to give an idea, there cannot be, there is no necessity that it should also, it has to have only cubic cell. I repeat, it can have any shape. If it is repeatable, it can always be used. There are only 14 ways in which atomic arrangement can be actually placed. These are called brevis lattices, only 14 ways, okay, in which one of them is primitive triclinic cells or tetrarhombic or rhombic, orthorhombic, all possibilities. But please remember, I am only using this for simplifying things. It does not essentially mean this is what the actual cell is primitive. Okay, there is a simple model to get this density numbers and all that. What we say, let's look at this 2 atoms. this is the corner. So we say, okay, to get an idea, okay, this is your center point of that. We say, okay, we have a sphere which is half the edge of the lattice. This distance is called A, lattice edge. A is the distance between two atoms and it's called lattice edge or lattice constant. Typically for silicon, this number is very important for silicon, 5.43 angstroms. This is only for silicon. For different atoms, different materials, this number will be different because the atomic arrangement when changes, only then the physical properties and chemical properties will change. Is that clear? Therefore, this is unique to silicon. Okay. Okay. Now, if this model, which is very popular, is called hard sphere model. Now, what we are trying to do really, why I am interested to get this so-called hard sphere model is, I am trying to see, is this unit cell has larger number of atoms as you thought you had when the silicon is put inside, let's say silicon structure. Is it heavily packed or loosely packed? If it is loosely packed, what will happen? The mobility will be larger, that means fewer hits it will get, and therefore, so a structure which is highly packed, that is the packing density is higher, will show more hits actually and compared to loosely packed. Now you will be surprised when I show you silicon. Silicon is having so many atoms inside the lattice as if, but its packing density is the minimum. Okay? And that's very funny. It's only a 34% packed, whereas FCC is 68%, PCC is 52% compared to this. Okay, where silicon has much more atoms, 8 atoms per cell, and in spite of that, it is loosely packed. Okay, so let's see why this number is different from us. This is called packing density. So let's calculate. To do this, I use this model. I say each has a sphere has a radius of a by 2 and it hits the next by another atom's sphere. Okay. So each atom is expanded to have a by 2 radius so that they touch each other. Is that point clear? So essentially what I am saying, like this, same way, of course now distance is not proper. So from everywhere the atom will touch the nearest neighbor half, a by 2, so spheres will be touching each other. What is the volume of unit cell? If A is the lattice edge, A cube. So now we were saying, if this is the A by 2 is the radii, okay, and there are n number of atoms, so volume of this sphere will be how much? 4/3 pi r cube multiplied by as many atoms you are talking about. Okay, this is the total number in volume, total volume occupied by spheres, and what is the net volume of the cell? A cube. So I define 4/3 pi r cube. So I define a term packing density as 4/3 pi r cube, then number of atoms per cell divided by a cube. R is a by 2 in this case. No, I am on the simple cubic. We start with the simple cubic. This is for simple. You are right. Yeah, what you are saying is true. If there is a, let's say this is BCC, okay. In the BCC case, it has a R which is a by 2 square plus a by 2 square plus a by 2 square under root of all this. Is that a diagonal? What will be R there? √3 kind of thing. So we can always calculate the nearest distance from the atom from this point to the, and that is called the R for the structure. Is that okay? Okay, so if I use this, and then R will be always expressed in terms of A, so A will not be required to know, even if we know it is 5.43, we don't need it because it will also come in A terms, so A will cancel. So all that number which we will get is by this method. So what is the trick about this? Why we are looking into this? Because we are trying to see which lattice is very loosely packed, lowest density even can, packing density. If that happens, one may say it has a larger possible mobility. Of course, there are other mechanisms of reducing mobility, but assuming with the only atomic hits, this may have the least of hits and therefore large. So two things we are worried about. One is the which way the electrons move, okay, and which lattice it is moving. So if we know these, then we will be able to probably hit mobility correctly, and if I get my mobility control, then I say fine, thank you, I have now current control. At the end of the day, please remember, all the material science I am doing is not for the sake of material science, which is next department, okay. We are doing it because we are worried that if my device has to work, I must know how it works and can I control it. And to that extent, I will spend my time on this, okay. Okay, I will not solve all of it. For a BCC, since this person was talking of BCC, the R is A by 2 whole square plus A by 2 whole square plus A by 2 whole square. Okay, this is root 3 by how much? 2 into 4, so 2A, okay. And this is the radius of the sphere, okay, this is the radius of the sphere. You substitute R there, multiply by this, and this density which I calculated for a BCC is around 68%. If I do the same thing for FCC, what will be R for FCC? A by 2 square plus A by 2 square under root of that. R for this will be only 2 of them. Actually this is not R, what is it? It is the actual distance, and by sphere model what is the R? R by 2. So we should actually say, because that, no sorry, this is R, but yeah, this is half will come because of what? Because the two sphere has the distance which is A, R total. The radius is only half of that. Is that correct? Half of that. Please remember, this is the distance, but this is the half of that is the R for that, sphere wise. So you calculate similarly for this, A by 2 by A by 2 square into this, and then you substitute on that this, the FCC will get 52% packing density. Sorry, 78, 74 or some percent, I'm not sure, but just think. Simple cubic will get 52%. And this will be packing density for FCC will be 74 or something like this, just calculate exactly. So what does that mean? That FCC, which has only atoms on the surfaces, have much higher packing density as compared to the BCC, which has actually one atom only at the center. Okay. So there is something more to it than what meets the eye. Is that clear? So this number essentially gives you how much packing atoms actually give you. Okay. Now there is difference between silicon lattice and all this cubic lattice is the following. This figure is slightly three-dimensional. I should have bought that lattice which is available in physics department. I don't have one. I could have actually shown you the, have they any time shown you that crystal structures with atoms at the corners? Okay. I don't have silicon lattice with me here, otherwise I would have shown you. To get you three-dimensional picture is difficult, so I am now doing a two-dimensional, and I will show you exactly what I meant. They are actually same silicon atom, just to separate the two parts I am putting dots. Okay. You also draw exactly the way I am doing, and these are not correctly distanced, so it may not look good at the end. If we are scaled properly, then we can do better. Okay, maybe one more. So there are two lattices I am talking, one with a larger this size and one with small. Actually they are same size atoms, but just to say there are two separate lattices I am talking. So what I am saying is, you please draw this. Do you get the point? This is one lattice which is smaller and the other is lattice because of the bigger size atom. Actually atom size is same, but just to show you two different lattice. So the way silicon lattice is, let's say this is one lattice. I have another lattice which is 1 by 4, 1 by 4 and 1 by 4. You get the point? There is another lattice which is getting inside this lattice by how much? 1 by 4, 1 by 4 and 1 by 4. 1 by 4 down, 1 by 4 x, 1 by 4 y. Okay, so diagonal 1 by 4, 1 by 4, 1 by 4. So essentially I may not be able to draw correctly, but still to show you, if this is your atom, so somewhere, okay, let's say from this atom you are going 1 by 4, 1 by 4 and also along this direction is how much? So somewhere let's say here, this is that lattice point. So two lattices of same kind but interspersed, that is getting inside by how much at every edge? 1 by 4, 1 by 4 and 1 by 4. 1 by 4, 1 by 4, 1 by 4. So the corner atoms actually gets inside. Is that correct? Corner atom of the second lattice is actually somewhere down here. Is that point clear? 1 by 4, 1 by 4 and 1 by 4 inside. Okay. From every corner, the other lattice will be able to give you one atom inside this cell. How many it can give therefore? For the simple cubic, how many atoms are getting? 1. From the surface, 3 more. And from the corners, you will get another 4 atoms inside. Okay. So what is the number of atoms in silicon then will be? 8. 3 from the surface, 1 from the corners and 4 which are 1/4 from each side. When they will enter, it will give you another 4 atoms. So silicon number of atoms per cell is 8. So essentially this, is that point clear? Why did I draw this? Essentially you say this is 1 by 4, 1 by 4, this is only 2 dimensional. So right now I am only showing you 1 by 4, 1 by 4. But if it is the third dimension, it will get inside and therefore you may say 2 interspersed lattices of silicon atoms going by 1 by 4, 1 by 4 inside from all sides constitutes the unit cell for silicon. Is that clear? That is essentially will give number of atoms for silicon is 1 plus 3 plus 4 per cell. How much will be its radii? A by 4 square plus A by 4 square plus A by 4 square under root and half of that to make it radius. Is that correct? What will be R for that? Half A by 4 square plus A by 4 square plus A by 4 square. This is for silicon. Is that okay? So what is the packing density, madam, will be? This is R. So what is the volume with this sphere? 4/3 pi r cube. How many atoms are there? 8. 4/3 pi r cube into 8 divided by A cube. That will be the packing density for silicon, and we calculated packing density for silicon is 34%. Is that clear? So which is highly dense lattice? FCC. Next is BCC. Okay. Then is simple cubic. But the silicon with so many atoms in has a packing density of 34%. and therefore you say silicon lattice is loosely packed lattice. Therefore the mobility in this is much higher than the sodium chloride and other similar crystals, because it is loosely packed compared to other lattices. Is that point clear? So this issue, people always say, itna atom hai, how can it be loose? So you can see why it is loose compared to other lattices, where the possibility of hit will be smaller, and therefore silicon will show reasonable amount of mobilities when transport occurs of electrons. Is that point clear? Why loosely? Why we are interested in this? Because we figured out, oh, aisa hai kya? That's great. So luck is in your favor. You never tried that you will get silicon loosely, because it looked as if it is very packed. Okay. But when we evaluated, we figured out, oh, electron can easily go, comparatively. And therefore we said silicon is used extensively in semiconductor industry because of its nature of giving transport, much easier transport. The other, of course, what is the reason I said about silicon, why we use? Because silicon has a natural oxide, which is silicon dioxide, which is insulator. Fantastic insulator, one of the best insulators world nature has given us, and is available in abundance. 1/3 of the earth crust is sand, okay, silica. Okay. And therefore, what is the other part which is filled up other than the earth, this silica? Water. Okay, that is the major. Okay. So is that this issue which I thought I would have skipped this, but I thought you should know this, because everyone asked me last few years earlier that, sir, itne atoms dikhte hain, or how can you say? I said, okay, here is a theory which allows me to think that way. Okay. Yes. But you can see from here, the other atom will be going from the other lattice side. उसका जो दो नीचे है ना, वो अंदर नहीं आएंगे ना, एक नीचे है ना, शिफ्टेड है ना, तो उसके के नीचे वाले के हैं, वो उसके नीचे वाले में जाए. See, since there is another lattice which is something going on like this, इसके जो है ये इसके अंदर नहीं आएंगे. Got it? Since it is going down, the lower portion of the 4 atoms will not contribute, because they will be part of the further lower down lattice on that. Is that? So only alternate. That means 4. Is that okay? Is that point issue? Why I said only 4? Because the other 4 will not be contributing to this cell, but will contribute to the lower cell. Okay? So this essentially says silicon is loosely packed and therefore may have, of course we don't know right now, but may have larger mobility. I am actually referring only right now the book from Streetman, so I repeat, I would request you actually buy at least one of the 3 books or 2 books. Of course any other book is good, but Streetman's book or Niemann's book, both are as good. There are certain things Niemann has given better, particularly the optical device part is much better there, but on an average they are copy of each other. Let's do, before as I say direction of the lattice, another thing which we are interested to know is something called Miller indices. Now let's look at a Cartesian coordinate. And let's say I have a plane something like this, any shape, a plane. So we say, let us say this, of course the plane, one important property of this is that it should be in the multiples of lattice edge, A, 2A, 3A, or half is not taken because half is essentially, if you double everyone then it becomes the same. So okay, this is A, this is A, this is A, let's say this is A. So this plane has these vertices. Okay. So what we do is, we figure out what is the intercept value of your plane on each axis. How much is intercept on the x-axis? 2a. 2a. How much is on the y? And how much on the z? A. Okay. So what we do is, if these are the intercept, the Miller indices are given as HKL, which are reciprocals of this intercepts. And A of course is then removed because A is common to all of them. So we say it is 1 by 2, 1 by 2 and 1. But as I say, 1 by 2 is normally not used. So what we will do is, this will be equivalent to what? 1, 1 and 2. So we say this plane is represented by HKL Miller index or indices HKL, which has a value of 1, 1, 2. Is that correct? Or essentially half, 1. Is that okay? If this would have been 3, let's say for the heck of it, then we would have said this is 3a, then this would have become 1/3, and then how much it would have become? Please take it, this is 6. So what will happen? 3, 2, 6. Is that okay? If one of them would have been 3a, it would have become this new indices. Okay. So this is how you can evaluate indices of any plane. Let's look at cubic structure again. Let's look at this plane. These are your axes. Tell me this plane I am talking. What are the intercept on each side? यहाँ तो 0, 0 मत बोले यार. नहीं. This is how much? No intercept. Okay, no intercept. How much is intercept on this? A. Why? This is cutting here, na, along this. Oh, sorry. Along the x there is no intercept. Along only z we have the intercept. Is that correct? So actually it is 0, 0 and 1. Okay. So HKL for this is 0, 0 and 1. Okay. So this is called 1, 0, 0. Of course, it can also be called 1, 0, 0. Why? Because x, y, z is arbitrary. I only said this is x. You may say that y and this x. So it doesn't really matter which way I look into. So 0, 0, 1 is identical plane to 1, 0, 0, but maybe on the back side or maybe on the other side, but they are same parallel planes. Is that clear to you? Same parallel planes which has only intercept with one axis but not with the other two. Is that clear? This is very important plane. 1, 0, 0 plane is very, very important plane. Okay. There is another possibility can exist in a normal lattice. Is diagonal cutting. How? What will be its plane? थोड़ा सोच के बताना. Which one? Please look at it. I am talking of this diagonal and this plane. 1, 1, 0. Is that okay? Can anyone see? 1, 1, 0 is this plane. The third possibility may be Now it intersects with all three axes by A, by A, by A. So what is the Miller indice for this plane? So the way we say, if this is your 1, 0, 0 plane, then the direction inside, that is normal to this plane, is called the direction of that plane. Is that clear? Direction. What does that mean? All 1, 0, 0 planes will be in this direction. Is that clear? All 1, 1, 1 planes will be, let's say, in this direction. So direction is always defined as normal to the plane itself. Why we want to have directions? Because in silicon lattice, there will not be only one layer of atoms, there will be number of atoms. All of them have, say, 1, 0, 0 plane, then the direction of crystal is 1, 0, 0. I repeat, if this is your, let's say, crystal I create, and if this plane has dimension, this is 1, 0, 0, then this direction is called 1, 0, 0 direction. Normal to that. That is, planes are stacked in this fashion. Is that correct? So this is called direction of the lattices or crystals. Okay. Why are we interested in? Because the way I will actually make crystals, okay, silicon crystal for example, there is a method called crystal pulling. From the melt, I will have a seed crystal and start pulling it. Okay, so it will start solidifying. So whatever is your seed crystal has the plane, the melt will form same planes as you go up. Okay, so direction is what? If I pull like this, so it is a 1, 0, 0 direction, and plane on the seed was 1, 0, 0. So the crystal is pulled along 1, 0, 0 to give planes of 1, 0, 0. By similar argument, I can do 1, 1, 0 or I can get 1, 0. In the case of bipolars, 1, 1 plane, 1, 1, 1, 1 plane is preferred plane. Please write down. In the case of silicon, BJT, 1, 1, 1 planes are preferred planes. And the case of silicon MOSFET, 1, 0, 0 is preferred. So what do you guess from this? That the material which I will use for MOSFET fabrication will not be good for BJT and vice versa. Is that correct? So those two technologies therefore will rarely be together, because what is good for one is not as good for the, of course it's not all that bad which I am trying to make, but essentially still preferred. Even if I get 20% advantage or 15% advantage, why leave it? Okay. It's not that I cannot make a BJT in 100 or 110 plane, any plane I can make. Okay. But the idea is, what is that I am talking, which number is varying more? The mobility. So we are looking for mobility terms, so we find for mobility point of view, 100 is ideal for MOSFET and 111 for BJT. Is that okay? So this is why we must look for, when I buy material, I must tell people what direction of material I am looking for or what planes I am looking for. Okay. So actually they are sold by these names, indice names, 100 oriented as they call, 100 oriented. Let's say later we'll say P type or N type with so much resistivity or so much defects, we'll add to that another things which we want. But first thing we have to say what orientations. So when I order a silicon, okay, so there is a term which I use often in devices or even in circuits. I actually cut very thin layers of this silicon and say they look like wafers. They are called wafers, silicon wafers. Typical thickness of silicon wafer varies. On what it can vary? Okay, I'll tell you a few things before we quit this plain business. See, this is silicon thickness. Okay, let's say it's a 100 oriented. Now, this thickness of the wafer varies with the diameter of the silicon. Varies with the diameter of the silicon. Why? Because silicon, if you see, many of the post office giving you some boxes, or in the it comes from a sea or air ship. There is a huge red color strips are fragile. Okay. That means easily breakable. Silicon is extremely fragile. The joke is, if you see, it may break. Okay, or it may not, but it states so. It's because it is very thin. Now question is, why do you want to have a very thin wafers? I mean, you could have a thicker wafer also. The problem is, in most cases, let's say this is 300 microns. Okay. By the way, I must tell you, 1 micron is 10 to the power minus 4 centimeter, and I will always use centimeter as my scale and not meters as you have studied earlier. In devices and electrical, we don't use MKS, we use some funny system. We also use milli-inches, mils as we call it. So we talk of nonsense, but that's the way we are, and that's we continue to be like that. Okay. So this is typically 300 microns. Okay. 300 micron, you can see from here, I am talking of around 0.3 millimeter thickness. Okay, 0.3 millimeter thickness. The problem, as I said, the device will actually come in first 5 micron maximum. तो 300 माइक्रोन थिकनेस है और डिवाइस एक्चुअल परफॉर्मिंग डिवाइस कहाँ होगा? फर्स्ट 5 माइक्रोन. तो 295 तो हटा दो ना उसको. तो वैसे ही 300 माइक्रोन itself is fragile. If I per se make uniform 5 micron is difficult to make, but let's say I make, before I touch it, it may break down into pieces. So I cannot handle thinner wafers. Okay. So this diameter, which will give, because of its density gives you stresses, it decides how much minimum thickness I have. So for example, for 2-inch wafer thickness, this or 3-inch dia, typically 300 microns wafers are used. But for 8-inch wafer, this is around 1000 microns. Diameter of the wafer. This diameter of the wafer is, yes, that day I showed you wafer sizes, big one. So the dia of a wafer increases, as it increases, thickness also has to be larger. Why? To support it, otherwise it will break. Okay, so what is essentially I am saying, since the device may come, and in newer devices even this 5 micron may not be required, you may require a micron or less. Okay, so the rest is doing nothing. It's only called physical support. Is that correct? It's called physical support. So it's wasted by us. So we are now trying different technologies in which this is reduced as much as possible, but nothing much we can probably able to do in this case. Is that okay? So these thicknesses are essentially governed by the size. 12 इंच होगा तो शायद 2 mm का thickness रखेंगे, क्योंकि इसको इतना हैंडल करना बहुत difficult. Otherwise just it will. Please remember, has any time you tried, you must have seen this, people who go to this frame making, they have that glass frames, glasses which cuts to a frame. What do? They put a scale and with a diamond scribe, they put lines. So why it breaks there? Every such crystalline material has something called planes. Just now I talked about. Some planes have much more distance compared to other. So if you give a stress, the material will go from this called cleavage. It will just cleave through that. So what he does it, he knows which is because the way it comes from them, this is the parallel. So just put a parallel line on that, put a stress, it just breaks from the same thing. So stress travel from top to bottom. So, same way silicon is also broken. If I scribe silicon and from the back side I roll with a rubber, it will keep pieces exactly the line I put on the top. Okay. That also through diamond scribers. Okay. So this fact that we need to scribe also helped by availability of plane, otherwise I cannot cut. For example, 1 plane is very difficult to cut. You get the point? 100, I know. 111 plane does not, it will go 57 degrees. Okay. So it is very difficult to cut a 111 planes by scribes as 100 or 010 kind of. Is that clear? That's what the tricks of the trade in actual devices. Okay. So we have seen that materials, their properties, their packing density, their possible atomic arrangement, possible thickness of silicon wafers, okay. Okay, so now we start with, that is bit of physics as I said. Of course we are still doing what I don't know, call it physics or otherwise. All of you have done this number क्या नंबर है ये कहाँ से आया? From using a quantum mechanics and any solid state material, for that matter any material, but for us it is solid state material, electrons, the way atomic arrangements, and will have electrons available to you, they can occupy only certain energy states. N is called principal quantum number. N is called principal, essentially it is in a Bohr's model which orbit you are looking for. N is equal to 1, 2, 3. So this is essentially we are talking that how each N we have possible energy. So what does it means? The energy levels are quantized. Okay, as I say, I will not go into Schrodinger equations and solving of that, but just to show you, energies are quantized. In solid state, this becomes even more important. The reason is, you can see from here, in silicon or any atom, in gas, atoms are free to move everywhere, so are the carriers can go anywhere. In liquid, they are bound by the vessel it contains, because there is a force on the surface tensions on the sides. But in the case of solids, all atoms are bringing each other together and together. So now, each electron associated with each atom is not just associated with itself, but is also in a way associated in the range of other atoms. Okay, so not only this will influence its property, but it also will be influenced by neighbors. Okay, closer you come, you have more problem which one it is contributing, and this leads to what we say further splitting of energy levels. Okay, why are we doing all this? Because we want to know, as I said you, is electrons available to us, what kind of they should be easy to move and what they cannot move. Okay, and is there energy gap between the two where they can easily move and where they cannot move? This gap of energy we call it as band gap. So we want to know what is the band gap of silicon, okay, because or any other material, and so that we will be able to say, okay, if I have an electron to go, at least it must have that much energy so that it is easy to move. If you have a larger energy, means what it actually has number wise. Larger energy means what does it by velocity it gets? Larger kinetic energy means larger velocities. Velocity is proportional to mobility. Is that clear? So essentially we are using indirectly the mobility terms in doing so. Is that clear? Okay, so I hope that time is up for me.